Welcome back to Unit 8. In Chapter 12, Section 4, we'll be solving exponential and logarithmic equations. With some of these equations, the variable will be part of the exponent, while others, the variable will be part of the argument of a logarithm. Starting in example 1, we will solve these two equations where the variable is in the exponent. And we'll start by using a method that we've seen before. Take a look at 3 raised to the exponent of 2x minus 7 equals 243. Since 243 is a power of 3, we're going to write both sides of this equation with the same base. We'll have 3 raised to the exponent of 2x minus 7 on the left and 3 to the 5th on the right. Now we can use the fact that exponents are unique to set 2x minus 7 equal to 5. Adding 7 to both sides, we have 2x equals 12, and dividing both sides by 2, we have x equals 6. So our solution set simply contains the value of 6. Now take a look at 4 raised to the exponent of 2x plus 1 equals x raised to the exponent of x plus 4. 8 is not a power of 4, so we cannot write 8 as 4 raised to some exponent. However, 4 and 8 are both powers of 2, so we can still write both sides of this equation with the same base. This time the base will be 2. 4 is equal to 2 squared, so we could rewrite this as 2 squared raised to the exponent of 2x plus 1. 8 is equal to 2 cubed, so we could rewrite this as 2 cubed raised to the exponent of x plus 4. Since we have exponents raised to another exponent, we will multiply. So on the left, we have 2 raised to the exponent of 4x plus 2, and on the right, we have 2 raised to the exponent of 3x plus 12. Now that we have the same base raised to two different exponents, those exponents must be equal to one another. That is, 4x plus 2 must be equal to 3x plus 12. Subtracting 3x from both sides, we have that x plus 2 is equal to 12. And subtracting 2 from both sides, we have that x is equal to 10. So our solution set contains the element 10. These two equations solved pretty quickly using a property that we already knew about exponents. But what happens when we can't write the two sides of an exponential equation in terms of the same base? We can use the one-to-one property of logarithms. The one-to-one property of logarithms states that for any positive real number b other than 1 and any real numbers r and s, if r is equal to s, then it's true that log base b of r is equal to log base b of s. And if log base b of r is equal to log base b of s, then it's true that r is equal to s. What this tells us is that we can take the logarithm of both sides of an exponential equation to help us simplify. This also tells us that if we have a logarithmic equation where the base is the same on both sides, then the arguments are equal to one another. Let's take a look at example 2. Here we have 5 raised to the exponent of x minus 7 equals 13. Let's start by adding 7 to both sides of this equation. This will give us 5 raised to the exponent of x minus 7 equals 20. Not only can I not write 20 as a power of 5, I can't write 5 and 20 as an exponent with the same base. So we'll use the one-to-one property of logarithms, specifically the first line. We could use the common logarithm or the natural logarithm to simplify this. For this example, I'll use the common logarithm, or log base 10. This gives us log of 5 raised to the exponent of x minus 7 equals log of 20. With our exponent as part of the argument of a logarithm, we can now bring it out in front of the logarithm as a factor. So we can rewrite this as x minus 7 times log of 5 equals log of 20. Now we'll solve for x. Dividing both sides by log of 5, we have x minus 7 is equal to log of 20 divided by log of 5. And adding 7 to both sides, we have that x is equal to log of 20 divided by log of 5 plus 7. This is the exact answer. So in exact form, we express the solution set containing log of 20 over log of 5 plus 7. We can also find a calculator approximation. Because we use log base 10, or the common logarithm. This is approximately equal to 8.861. Let's take a look at a similar example. In example 3, we once again have an exponential equation that we need to solve. We will first find the exact solution and then approximate the solution to the nearest thousandth. We'll begin by isolating the term that has the exponent. We'll subtract 35 from both sides. This gives us 4 times e to the x minus 3 equals 72. And dividing both sides by 4, we have that e to the x minus 3 is equal to 18. Now, since we cannot write 18 as a power of e, and we cannot write e and 18 as a power of the same base, we'll use our logarithms and take the logarithm of both sides of this equation. Since my base is e on the left side, let's use the natural logarithm, or log base e. That will give us the natural log of e to the x minus 3 is equal to the natural log of 18. Now we can bring our exponent out in front of the logarithm as a factor. So we'll have x minus 3 times the natural log of e equals the natural log of 18. The natural log of e is simply 1 because we have log base e of e. So this is simply x minus 3 equals the natural log of 18. And adding 3 to both sides, we have x equals the natural log of 18 plus 3. That's our exact answer. Our solution set contains the value 3 plus the natural log of 18. But we can also find a decimal approximation. 3 plus the natural log of 18 is approximately equal to 5.890. Now let's try solving some logarithmic equations. Here in example 4, we have a logarithmic equation rather than an exponential equation. The second part of the one-to-one property of logarithms tells us that if we have two logarithms with the same base set equal to one another, then the arguments must equal one another. In this equation, both sides have a log base 10, or the common logarithm. So it must be true that the arguments x squared plus 3x minus 11 and 9x plus 5 must equal one another. Now we'll solve for x. Subtracting 9x from both sides of this equation, we have x squared minus 6x minus 11 equals 5. And subtracting 5 from both sides, we have that x squared minus 6x minus 16 equals 0. Now we have a quadratic equation in standard form, and we can factor it. This factors as x minus 8 times x plus 2. And using the zero factor property, we find that x minus 8 can equal 0, or that x plus 2 can equal 0. And solving these two equations for x, we have that x is equal to positive 8, or x is equal to negative 2. Now, with logarithmic equations, it's very important that we check our solutions. A logarithmic equation requires that the argument is a positive number. So it's important that our values for x create positive numbers inside the logarithm. Let's first check our solution, x equals 8. If x is equal to 8, then x squared plus 3x minus 11 is equal to 64 plus 24 minus 11. That's clearly a positive number, so 8 is in the domain of the logarithm on the left side of the equation. Now let's test out 9x plus 5. If x is equal to 8, this is 72 plus 5, which is also a positive number. So the solution x equal to 8 is in the domain of these logarithms and is okay as a solution. But now let's check x equals negative 2. If x is equal to negative 2, then x squared plus 3x minus 11 is equal to 4 minus 6 minus 11. That's a negative number, so this is not in the domain of the logarithm on the left side of the equation. So negative 2 is not okay as a solution to this equation. Now we know that the solution set to this equation contains only the value of positive 8. Let's solve another logarithmic equation. Take a look at this equation in example 5. Unlike in example 4 where we had a logarithm on both sides of the equation, we only have one logarithm. And if we add 5 to both sides of this equation, we have log base 3 of 2x minus 1 equals 3. We have a logarithm on one side set equal to a number. So in this case, we actually don't need to use our one-to-one property of logarithms. We can simply switch to exponential form. Switching from logarithmic form to exponential form, we have 3 raised to the power of 3 equals 2x minus 1. 3 to the third is 27, so we end up with a linear equation to solve. Adding 1 to both sides, we have 28 equals 2x, and dividing both sides by 2, we have 14 equals x. Let's double check our solution. If x is equal to 14, then the inside of the logarithm, 2x minus 1, would be 2 times 14 minus 1, or 28 minus 1. This is clearly a positive number, greater than 0, so 14 is in the domain of the logarithm. In other words, 14 does check out as an okay solution, and our solution set contains the value 14. Let's continue. We'll solve two more logarithmic equations. In example 6, our logarithmic equation contains two logarithms. But even if we put them on two different sides of the equation, we would not be able to use the one-to-one property of logarithms because we have that constant term 5 getting in the way. Since our two logarithms have the same base, they are both log base 3, we can combine these as one logarithm using the product rule. This is equal to log base 3 of x times x plus 18. Now we have a single logarithm set equal to a number, or log base 3 of x squared plus 18x equals 5. Writing this equation in exponential form, we have 3 raised to the 5th power equals x squared plus 18x. And we can simply solve for x. 3 to the 5th is equal to 243. So we have 243 equals x squared plus 18x. And subtracting 243 from both sides, we have 0 equals x squared plus 18x minus 243. Now we have a quadratic equation in standard form, and we can use our quadratic methods to solve. In this situation, we can factor. We have 0 equals x plus 27 times x minus 9. But we could also solve this equation using the quadratic formula if you prefer. Using the zero factor property, we have that x plus 27 can equal 0, or that x minus 9 can equal 0. And solving for x in both of these equations, we have that x is equal to negative 27 and x is equal to 9. Let's double check both of our solutions and make sure that they are in the domain of each of these logarithms. First, if we plug in negative 27 into this first logarithm, we'll have log base 3 of a negative number. We can't have that, so negative 27 is not in the domain and is not a solution to this equation. However, if x is equal to 9, we have log base 3 of 9, which is perfectly acceptable, and we have log base 3 of 9 plus 18. Again, a positive number, so 9 is an acceptable solution. The solution set to this logarithmic equation contains the single value 9. Let's go on to one last example. In example 7, we again have two logarithms, but we also have a constant term of 2, preventing us from using the one-to-one property of logarithms. Let's use the quotient rule instead to combine these two logarithms into a single logarithm. Using the quotient rule, we have log base 4 of the quotient 7x minus 1 over x minus 4. And switching this equation to exponential form, we can rewrite it as 4 squared equals 7x minus 1 over x minus 4. That is, 16 equals 7x minus 1 over x minus 4. To solve this equation, let's multiply both sides by x minus 4. This will give us 16 times x minus 4 equals 7x minus 1. And 16 times x minus 4 gives us 16x minus 64. Now we have a linear equation that we could solve for x. Subtracting 7x from both sides of the equation gives us 9x minus 64 equals negative 1. Adding 64 to both sides of the equation gives us 9x equals 63. And dividing both sides by 9, we find that x is equal to 7. I'll leave the details to you of double checking the solution x equals 7. That concludes this lecture video on how to solve exponential and logarithmic equations.